My dear students, we have seen what is exactly magnitude comparator. We have designed 1-bit magnitude comparator. Then we have designed a 2-bit magnitude comparator. But in general, we may require to have a comparator which is supposed to compare 8 bits, 16 bits, 32 bit and 64 bit. So what we need to do is we will analyze this for a 4-bit magnitude comparator. Then we can analyze, we can apply the same analogy to any bit number comparator. That is what exactly the idea behind going for 4-bit magnitude comparator. For any comparator, as we know, the comparator will be having two inputs. Two inputs is variable A and variable B. Variable B. This is a bus. This is a bus. It may be 4 bits of each, or it may be 8 bits of each, or it may be 16 bits of each. If I draw a line with a cross line, if I say that it is a bunch of 4 wires. If I draw a line, if I say with a cross line 8, it is a bunch of 8 wires. That bunch of wires is called a bus in digital logics. Okay. So there will be a bus. What is A stands for here? It is a combination of A0, A1, A2, A3. What is B stands for here? B0, B1, B2, B3. Okay. So it is a 4 lines. Now what just in this case what exactly I am trying to do is just I am taking an example of having only 4 bits. So I am not bothered about 8 bits. But what we did so far is 1-bit comparator we did it, right? And we did for 2-bit comparator, okay? And we are going for 4-bit, and from there we are going to generalize n bit, okay? So case 1 I have seen, case 2 we have seen, case 3 we are seeing, case n is in general, okay? How exactly deal with it? So generally we will be having how many outputs? 3 outputs. What are they? A less than B, A greater than B, A equal to B. Okay. So this we can write it as A greater than B. Some again is some XYZ we can represent it here. So here it has shown that A greater than B is should taking is X, A equal to B as Z, A equal to B as Y. Okay. So 1 0 0 means A less than B, 0 1 0 means A greater than A equal to B, 0 0 1 means A less than B. So in anywhere in any order we can take it. Okay. As an example, for a 4-bit magnitude comparator, this is how XYZ are represented. Okay. So actually here as per the slide, A greater than B, A greater than B is X. So this is X. A less than B, A less than B is Z. Okay. And A equal to B is Y. Okay. So this is just I have written, but what exactly is there in this slide is this. Okay, that is not an issue. You can use PQRS, okay, MNO, whatever it may be. Now if A equal to B, when A equal to B, A equal to B is possible. Let's suppose 0 1 0 0. This is also 0 1 0 0. What is the meaning of that? A0 B0 equal, A1 B1 equal, A2 B2 equal, A3 B3 equal. Okay, then only I can say A equal to B. So how to do 1-bit comparison? We have seen. In 1-bit comparison, what is the equality that we can get it? So let's suppose you have AB and Y. Let us looking for comparison. 0 0 0 1 1 0 1 1. For 0 0 1, for 1 1 1, for rest of the things it is 0. This is not a gate where it is XNOR operation or complement of XOR operation. Okay, this is XNOR operation or complement of XOR operation, which is called A bar B bar plus AB. This is also known as A bar B plus AB bar whole bar. Okay, so what exactly that is? I can say that A equal to B is possible for any number of bits for that matter. So for A equal to B is possible, which is we are calling it as Y, provided what exactly your T0, what exactly if AI and BI are equal, that is T0 is 1, what is T0? Here we are writing it as T of I is A of I XR with B of I complement. Okay, so in general what I can say here is if A0 exclusive odd with B0, if you complement it, if I get 1, then A1 exclusive odd with B1 complement of it XNOR operation is 1. That means this means A0 equal to B0. This means A0 equal to A1 equal to B1. So on and so forth I can write. Then I can say that A equal to B. So what is further? If A2 exclusive odd with B2 complement is 1, then what is the meaning of that? A2 is equal to B2. Similarly, A3 exclusive odd with B3 whole complement. So if this is 1, this is 1, this is 1 and this is 1, then y is 1. That means if all are 1s, then what I can say that A equal to B. So the idea is very simple, and we are trying to find in general expression for the what exactly expression for A equal to B, A less than B, A greater than B. So let's say for example A less than B, A greater than B, if at all you want to check it out. How we can do that is very simple. How is, we will come from the higher order bits. Let's suppose A3 is 1. Say A3 0. Say for example what I can do is I can take an example number and I can check it out. Say for example if I have A3 1 and B3 is 0. So doesn't matter whatever may be the next bits. This is let's say A3, A2, A1, A0, B3, B1, B2, B1, B0. Let's say B3 is 0. Some numbering is there, say 110. If B3 is 0 and A3 is 1, simply I can say doesn't matter whatever may be this bits, doesn't matter whatever may be this bits, I can say simply A greater than B. Right? If these are equal, then we need to look at A2 and B2. If those are equal, next I need to look at this two. If those three are equal, then I need to look at this two. So this is how exactly. The meaning of this is, okay, if first three MSBs are equal, it is based on LSB. What is the meaning of that is 1 1 1 1 0 1 1 1 1. Let's say this is A and this is B. So in this comparison, let's say this is AB. If that is the case, what we need to do? We need to look at these two. These two are equal. These two are equal. These two are equal. So what is that equality? Equality is XOR operation. So what is XOR operation? Complement of XOR operation. That is XOR operation. So T1 means A1 B1 equal. T2 means what is T? T of I, we are representing it as A of I exclusive order with B of I whole complement, or it is A of I XNORed of B of I. That means this will be 1 when both are equal. Say T of 1, T of 0, T of 2, T of 3. This will be 1 when both are equal. That is XNOR operation. So first three digits are same. Based on the LSB digit, I can say which is small or which is large. Okay. So see here, we can also write here. How I will write here is, for example, A less than B. When it is, when T3 means these two digits are same. T2 means A2, B2 are equal. T1 means A1, B1 are equal. Now A is 0, B is 1. So it is A0 bar, B0. Or under what circumstances exactly A less than B is possible? First 3 equal based on this digit. First 2 equal based on these 2 digits. First only one digit same based on last 3. So this is how exactly we try to do it. For example, next, what is the possibility? Only first 2 equal. If first 2 are equal, that means say these 2 are only equal. What is that? I can say T3, T2. But I am depending on based on this A1, B1. I can say if A1 complement B1, that means A less than B. Similarly, only first digits are equal. Means what exactly? T3. What is T3? Equivalence we are checking. T3 is equivalence. T is a will tell you T equivalence. If A0 B0 equal, A1 B1 equal, A2 B2 equal, A3 B3 equal, A equal to B. Okay. T3 says T3 is nothing but what? T3 is nothing. T of I is A of I exclusive of B of I whole complement. That is XNOR operation. So T3 means A3 B3 equal. So now what exactly that we are trying to do is, if T3 is equal, we are try to decide less than or greater based on the A2 B2. So I can say if it is A2 bar and B2, A2 bar B2 means A less than B. Okay, let's suppose we are deciding based on first digit. So deciding based on first digit is possible. Okay, with what is that? Just by checking the MSB bits. Let's say if A3 is 0, whereas B3 is A3 is 0, whereas B3 is 1, I can say A less than B. Doesn't matter whatever may be the A2 B2, doesn't matter whatever may be the A2 B2, A1 B1, A0 B0. Okay, are you getting what I'm trying to say? So if A3 is 0, B3 is 1, I need not look at rest of the bits. If first A3 B3 are equal, then I need to look at this next bit. If these two are equal, next bit. If these three are equal, next bit. So what we are trying to do is, we will be comparing say A3, A2, A1, A0, B3, B2, B1, B0. Okay, A1, A0 here. Now what is, if we'll compare these three, if this is 1, this is 0, doesn't matter these three, I can say A greater than B. If this is 1, this is 0, I can say A less than B. It is like this. Next, if these are equal, no, let us suppose these are equal, maybe both ones or both zeros. Then we look at this. If A2 is 1, B2 0, I say when this is equal and this is, what is this A3 B3 equal? T3. Then A2 1, B3 0, A2 bar B2. Or likewise we will be having all possible combinations that will give you the expression in general, direct expression for comparator. Okay, from this we can implement, from these expressions we can implement what exactly known as a 4-bit comparator. If you have a 4-bit comparator, from 4 bits to 4-bit comparators, I can get 8-bit comparator. I can, by using two 8-bit comparators, okay, I can get 16-bit comparator. By using 16-bit comparators, I can get 32-bit comparator. Likewise, we can implement any order of higher order comparators from the lower order comparators. Let us look at comparator. This is T3. What is T3? A3 equal to B3. So what we are getting here? What is this exactly? Is A3 B3 plus B3 bar A3 bar. Similarly T2, T1, T0. Okay, from the expression for A equal to B, A greater than B, A less than B, A equal to B, this diagram is obtained.